Hello, my name is Xianping. I'm a postdoc at Rutgers University. Our project is called Control Code Design Optimization Framework with Mixed Fidelity Fluid and Structure Analysis. As a part of this project, my presentation focuses on the control code design modular. The aim of our research is to develop a computationally efficient optimization framework for the design of floating offshore wind turbines. Our specific aim is to utilize high-fidelity error structure tools and to derive reduced order models directly from those high-fidelity tools. Our project is executed by a multidisciplinary team consisting of Rutgers University, University of Michigan, Brigham Young University, and NIE-AIR as our primary partners. We are also collaborating with the National Technical University of Norway and the Technical University of Denmark. Traditional wind turbine designs frequently rely on the design and optimization of each subsystem in an independent manner. This is often referred to as a sequential design approach. Today's floating offshore wind turbines are highly coupled systems of electrical grid, power electronics, and different structures and mechanisms interacting in a dynamic fusion with the surrounding air, water, and soil. In this project, we consider a control code design approach, taking into account the interaction between the subsystems and applying control concepts in the design process, with the aim of obtaining the more optimal solution. In this presentation, I will do the overview of control code design approaches first. Then three control code design methods developed in our module will be introduced one by one. That is the low-fidelity model-based control code design, reduced order model-based control code design, and combined fidelity approach for control code design. In the reduced order model-based control code design, I only do a brief discussion of the reduced order model. For detail, please see the presentation on the reduced order model and the controller modular. Similarly, I also do a simple introduction on the combined fidelity approach for the control code design, since it is included in the aerodynamic modular. Here I'm listing the three control code design optimization approaches. The so-called low-fidelity model-based control code design is developed using modeling based on OpenFast. The reduced order model-based control code design approach uses the reduced order model. Finally, the so-called combined fidelity approach combines modeling of OpenFast and the MAC framework. Using an OpenFast-based turbine model, a control code design framework is developed as shown in the figure. In this framework, aerodynamic parameters are selected as design variables. For example, blade chord and twist distribution in aerodyne can be varied. Next, the structure model is updated and the controller is retuned to the new system. The process is repeated until the optimization criteria is reached. To demonstrate the low-fidelity framework, an example design optimization was conducted. The objectives are to maximize the annual energy production and to minimize mass. The constraints are defined for the ranges of design variables and for maximum structural loads. For the optimization, we evaluated the annual energy production using design load case 1.2. 22 beams are defined for different mean wind speeds, with their probability fitted using a Weibull distribution as shown on the left. The damage equivalent loads are also evaluated. Design load case 6.2 is also used to evaluate the optimal strength of turbine structures under a parked condition. A genetic algorithm method is used to approach this nonlinear and complex multi-objective design optimization problem. The generated Pareto front is shown on the left. In this case, it is shown that the mass of the blade is easier to reduce compared to increasing the annual energy production. As an example, two designs along with the baseline design are illustrated on the right side. The chord distribution has much more variation among different designs compared to the twist distribution. The reduced order model-based control code design framework is currently under development. A key component of this approach is the reduced order model itself. The model is briefly described here. For details, please see the presentation on the reduced order model and the controller modular. Traditional wind turbine controller design is based on a simple dynamic model where only the speed of generator is of interest. Therefore, a first-order model like the one displayed here is sufficient. This is the case of the legacy wind turbine controllers and the recently proposed Roswell controller currently being tested on a small-scale wind turbine at the University of Maine. As exemplified in the motion picture on the right, innovation concepts of floating wind turbines tend to have very long and flexible blades and in general a slender and flexible structure. In our approach, we aim to make the wind turbine extract the desired wind energy while reducing as much as possible the mechanical fatigue of the structure. To do so, we consider a multi-degree of freedom model to capture the dynamical behavior of the main structural components of the system. Here I introduce the reduced order model to be used through the controller synthesis. This model aims to capture the dynamic behavior of the main structural components of the system, namely the AP and the dynamic vibration of servers, and tower and the nacelle, and the drivetrain and the rotor, as shown in the figure on the right. The equations of motion are derived using the Euler-Lagrange mechanics, assuming interconnected mass spring damper elements. Euler-Lagrange equations are written in the terms of kinetic energy and both conservative and non-conservative generalized forces. The contributions of conservative forces are related to the potential energy of the system, while the contributions of non-conservative forces are related to the aerodynamic and hydrodynamic effects, damping mechanisms, and forces made by actuators. The aerodynamic coefficients of the rotor blades are assumed to be a function of both the pitch angle and the tip speed ratio of the blade. The parameters and coefficients that fit the reduced order model come from other submodulars. Actuator dynamics and nonlinearity, such as magnitude and rent saturations, are also considered in the modeling process. Each degree of freedom of the presented model can be enabled or disabled to analyze a specific set of degrees of freedoms of the interest. For example, the platform degree of freedom can be disabled to study the model of fixed base wind turbine. Although the derived reduced order model is intrinsically nonlinear, it can be linearized about an operating point to proceed with the design of the control system. Based on the developed reduced order model, a sample of the design load case 1.2 is used as the wind input of the reduced order model, with the wind speed in x direction shown as the left side figure. The variation of the generator speed is reduced greatly using the H infinity and the H infinity plus reference governor developed in our modular. Also, the structural tower rotation is also mitigated by the new control strategies, which could reduce the structural fatigue loss. Because it is already quite computationally intensive, our high-fidelity simulations are limited to steady-state conditions. This provides an accurate description of how the power production is distributed along the rotor. However, when designing a wind turbine, many unsteady load cases also need to be evaluated. That is, mainly to guarantee the integrity of the structure in events including various turbulent wind, gusts, and so on. The approach that we present here provides a way to combine steady high-fidelity simulations and unsteady conventional simulations into a single optimization. The result is a design that is both optimal from the perspective of the high-fidelity aerostructure solver, but also complies with the design load cases defined in the standards. Without going into details, the algorithm we designed works in two stages. In the first stage, in green, we perform many open-thrust simulations to determine the extreme loads and the fatigue loads on the turbine for a given design. In the second stage, in red, we keep the extreme and fatigue loads constant, and we optimize the turbine design. This procedure is repeated until convergency, which we generally observe after 2 or 3 iterations. Finally, This algorithm also integrates well with control co-design since we can re-optimize the turbine controller as desired during the first stage. In conclusion, multiple control co-design optimization approaches are developed for the floating offshore wind turbines. The low-fidelity model-based control co-design is demonstrated and integrated into the control co-design modular. The reduced-order model-based control co-design is introduced. The combined fidelity approach for the control co-design is also introduced. In the future, we will complete the reduced-order model-based control co-design and integrate it into the control co-design modular. Also, combined fidelity control co-design will be integrated in the modular. Before closing, we would like to thank Professor Marcel Gassessens for the opportunity to participate in the athletics program. Special thanks to Dr. Dylan Temple, Dr. Carol Neros, Madeline De Fuentes, Michelle Olsen, and the entire athletics team for their support. For questions related to this presentation, please use the contact shown. For questions related to the overall project and our technology to market activities, please contact the PI at the address shown. Thank you for attending my talk, and please check out other technical presentations in our booth. Here are some additional references. Thank you for watching this talk.